and also share my screen. And there we go. Here is our lab number 3, and you can see the name, it's about tension. So in this lab, we have to put one specimen under tension, but before I show you the exact lab, I just want to put things in context. I know now your second semester, you have gone through the statics course and probably know what does mean tension and compression. So I just want to show you in some of the structures, probably you've seen those structures. I want to show you where tension happens. Okay. So for example, this is a steel bridge, very, very common, not for cars, but typically for railway and for sea train. For example, if you go to the southwest of Calgary, you will see a couple of those guys in the southwest of Calgary or southeast. Called truss bridge. So it's made out of steel members, like we call them top chord, bottom chord, diagonals and verticals. And so I just want to make sure that you guys understand that these members, you can see I labeled them with the forces in them. So for example, the vertical member in the middle, this is a zero member. It means under vertical loads, it has no force, zero member, no force at all. Okay. And those first diagonals, like this diagonal right here and this one, because of their orientation under gravity load, they will be in tension. Your last chord, which is this one here, last diagonal, I'm sorry, this one right here, it will be in compression. Also, this one will be in compression under gravity load. Okay, so let me show you more about tension and compression. So this is very typical, very, very typical bridge construction, which is made out of beams, but since the beams are heavier than normal beams, so we call them girders. So it will be series of these girders. You can see those green ones, we call them girder. You can see the span between those piers, like this one and this one right here. They are simply supported and under gravity load. So if my load is going down like so, okay, so you will see the bottom chord will be in tension and the top chord will be in compression. So bottom chord in tension, top chord will be in compression. Last example of tension and compression, which is reinforced concrete. So you guys remember that last semester you study concrete technology. Concrete is really good material. It performs very well in compression, but very, very poorly in tension. If you remember this discussion, please give me a thumbs up. Concrete is amazing in compression, performs very bad in tension. Now, what happens is if you subject a beam like this beam right here, and I make the beam transparent so you guys can see the anatomy of the beam. So if you think about those as support, so this point is support point, and this point is also support point, and the loads are in yellow. So you will see just like this girder here, the bottom chord will be always in tension. If concrete is bad in tension, what can we do? If concrete is really bad in tension, what can we do? The answer is on the slide. So what we do is we simply add those 3 bar in the tension side to take care of all the tensile stresses. So you can see here, you've seen several locations where tension exists in our structures. Time now to start our test, okay? So our test, we do it according to something called ASTM. Some of you may know what does it mean, ASTM. ASTM stands for American Standards for Testing Material, which is really comprehensive standard for testing all the material you may think of, steel, aluminum, copper, plastic, and other materials, okay? In Canada here, and my observation is sometimes we have our own standards, but sometimes if we haven't developed our standard yet, we use the American standards for many, many things. As an engineer, I can tell you that. So this is one of those things that we use the ASTM. Now, our test has a designation, so the name of this test or number called E8, and please remember this, E8, because this is one of the quiz questions. It will ask you what is the ASTM designation of the test. And so the ASTM E8 is a test designed for testing metallic materials in tension, okay? And it can be used for steel or aluminum. Same test, exactly the same test. Let me show you what's the objective of the test. So we're not doing the test for the love of the testing. We have objective. So the objective is to understand the behavior of the steel or the aluminum under tension. And through the test, we want to find those few things. I'm going to box them out for you. Number one, we want to establish the relationship between stress and strain. We need to find some values for something called yield strength, some values for the tensile stress. We want to also find the modulus of elasticity, very important. And then finally, we want to find the rupture strength. So you can see, I'm going to show you in how we can find all these numbers or observation from the test. Okay, so let's go to this slide here. So this slide here, it tells you the shape of our specimen. Remember the specimen, for example, in Sharpie, we just seen this test like a few minutes ago. It's a kind of a machined specimen. However, also here we have a machined specimen, but a different shape. You can see here the different shapes. So according to the standard, you can use one of these shapes to test your metal. However, at SATE, we always use this one on the very left, okay? The one on the very left, okay? So really, it's kind of a bar, a steel bar, but we machine it to create this kind of extrusion or head. You can see here, it has a head on each end. And shortly, you will know shortly why we do that. Why do we shape our specimen this way? Okay, so our specimen will look like so kind of machined bar. Now, with the specimen, we are trying to measure a couple of things. We are trying to measure the stress and strain. So the stress is measured by the machine itself, while the strain, we need a device called, you can see the name, called extensometer. And this extensometer, it measures for us the strain. And this is on the right picture. It is how the machine or this little device attached to my specimen. So which means when I apply tension here, like this way, when I apply tension this way, you guys probably can guess what happens. This specimen will elongate, will increase in length. And since we're attaching this extensometer, we're able to measure the change in the length. And the change in the length, it is something we call it strain. All right. So now you'll understand why do we simply shape the specimen this way. So this is a real specimen that we use at SATE, okay? And you can see it is machined in a way, so it has a head at each end. Why is that? Because we have to grip on this ends, okay? We need to grip them on them. And then the machine will apply tension. You can imagine how hard to grip on something that doesn't have a head. Now, also on the left side, you can see here we have an attachment. So I want you guys to look at the picture on the middle. So the picture on the middle shows you the gripping attachment. It's an attachment that we place our specimen so we can use in the machine and we apply tension. So this is before we close it, and the far picture on the left, it's after we add it together. The purpose is to be able to hold very strongly on the specimen. Okay? I can tell you without this one, the test is almost impossible. This attachment here allows us to grip on the specimen very, very strongly. Now, there are some measurements you have to do before we start the test. So before we even start the test, what we do is you can see here my specimen. You can see what we do is we notch. We notch here 2 notches on the specimen with some tool that precisely it makes the distance between the 2 notches exactly 2 inches. 2 inches. Think about it like you have a kind of a needle that the distance between the 2 needles is exactly 2 inches, and we use hammer to notch into the specimen. We call this distance L0. That's our distance before L0, before we start our test. Together with the length, we also measure the diameter of the specimen very, very precisely. And for this purpose, we use this thing. Anyone in my class knows what do we call this thing? This is a precision measurement machine called caliper. And the caliper is, if you talk to any machinist, they will have this caliper. It measures distance to a fraction of a millimeter. Fraction, like let's say 100 of a millimeter. All right. So as I said, we have to do some measurement before we start. We simply measure the diameter. We call it D node, and always your L node will be 2 inches, like 50.4 or 50, I think. 50.1, 50.1 millimeters, 2 inches. All right, so what's next? So here is what's happening next. You can see here, here is the gripping attachment. You can see it has 2 parts, and it grips into the head. We have it on the top, also on the bottom, right here. And then finally, we place everything into our machine. So our machine, what it does, it's simply using the gripping attachment, which is gripping into the head of our specimen. It tries to pull this way, and it tries to pull this way, applying tension to our specimen. Okay. And you can see, where is the extenometer? It's right here. So this device right here, it simply measures the strain, and you can see there is a cable, and this cable is connected to our computer, where it reads all the extension or the elongation, and we can draw the relationship between the stress and the strain. Now, there is some test details. So as I said, this test is done according to ASTM E8, and so everything is precisely defined. For example, what is the load rate? Am I loading, for example, my specimen in 1 hour or 2 hours or 3 hours? So there is a specific load rate. And for example, watch please number 6. So I want you to read number 6. So number 6, it tells us how often we record the reading. So you can see here, we record the load and the elongation every 500 pounds, which is 2.2 kilonewton, and that's for steel. However, for aluminum, we measure every 200 pounds, and until we reach the yield point. As I said, everything is settled here. Please take your time, read all those test procedures. Not really hard to read on your own. However, here is the test. Okay, so this is our test picture, and this machine, by the way, I'm not sure if I have a full scale for the machine, but the machine is called UTM, Universal Testing Machine, because we're not only testing this machine for tension, but we can use it for tension, compression, bending. All we have to do is just change this jig right here. You can see this jig right here. You can attach or disattach. So it depends on what we're trying to do. We change the attachment of the machine, but we can test tension, compression, or even bending in the same machine. That's why it's called Universal Testing Machine. Now, what I'm going to do right now, I'm going to switch to my PowerPoint, because on my PowerPoint, I have my video, because I cannot have a video on YouTube, on PDF. So I'm going to switch here to my PowerPoint, and I will show you the video. Okay, let's do that. Yeah, go ahead. I want to stop the video right here because I want to ask you, like you can see here, Steve Ball, and I know probably you know Steve Ball. Probably he taught you the concrete lab. Okay, so Steve Ball, he was helped me to take this video footage last year. And at some point you can see we had to remove this extensometer. Can you guys guess why is that? Any thoughts of why do we need to do that? At this point, not from the start, not from the start. At some point, the machines keep increasing the load, and at some point we have to remove it. Anybody can guess why is that?
Is it because you're almost reaching the point of failure and then it's going to break and it could damage the device if it's on there?
Perfectly said. We're very close to failure, and if we leave this device until it fails, then we break it. So by the way, so you know, I know it's not in the video, but same time that we have a computer, so all the data is simply logged into the computer, and dynamically on the computer you should see the graph between the stress and strain. Remember, and I'll show you the graph shortly, but we're trying to establish a relationship between two variables, which is stress and strain. So the graph will develop ahead of you, and you will see visually when the specimen is close to failure. Even the machine will tell you, remove it now, remove it now. Okay. So at this point of time, we have to go and open, which is not really an easy or safe process. We have to quickly take out this device, and then we continue the test. Now, please watch what happens. So I want everyone, please look at my cursor. So my cursor is right here, and I want everyone to focus where my cursor is. Right now, please, right now, right now. So what happened here is, as I said, we remove this device just before the failure, but as soon as we do that, there is something's going to happen. And if you notice from the video, the cross section of the specimen will get smaller and smaller, creating a neck, okay, a neck. This part called necking, and then right after necking, what happened is the specimen will simply snap and will fail. Now, let's see what happens, what we have to do. So as soon as failure is happening, and you can see this is how it looks like in a kind of a zoom in. Look at what happened. Like I want you to look at this profile. Probably it's easier to see on the profile. So I want you to look at the profile here, what happens. You can see it's kind of a straight and then it bends. It means the diameter right here is smaller than this diameter, okay? And that's what's called the necking. Now what we do next is we put things together as much as we can, and finally we measure two values again. We measure the final length between the notches we made before the test, and we also measure this smallest diameter right here, call it D sub F. F denotes to the final, it means after the specimen has failed. So you can imagine, we have a measurement before, we call it L0, we have measurement after, and we call it LF and DF. And we use the same device right here, which is the caliper, to measure the L and the D very precisely. And remember, if we were to repeat this D several times, all you have to do is just get the average. For example, I measured this 3 times, and let's say 40 point, not 40, sorry. Let's say 8.5 and 8.51 and 8.52. You guys know what to do. We always take the average if we were to repeat the same measurement over and over and over, okay? Now here is some math I want you to understand. Number one, I want you to remind you, because that's not new, I want you to remind you that the stress is calculated by dividing the force in Newton divided by the cross-section area in millimeter square. So if the machine reads the force, and we're able to measure D node, like the initial diameter, the machine can simply find the cross-section area, which is not super science. It's simply multiplied by D node square divided by 4. This is the cross-section area. If you divide the force by the cross-section area, you will get the stress in MPa or megapascal, which is equal to Newton per millimeter square. Those are the units. Number two, I need to remind you of the meaning of strain. So the strain is epsilon, which is simply L minus L node divided by L node multiplied by 100, which means it's a percentage. So it means unitless. So the strain is unitless. How you do it? You divide the change in the length by the original length, multiply it by 100, so you can find as a percentage. Finally, the modulus of elasticity. And the modulus of elasticity, I'm not sure if you know about it, probably you do. It is the slope of the line between stress and strain. I'll show you this later on. But you guys remember the slope of any line. If you have a line and you want to find the slope of the line, if this distance is equal to y and this distance is equal to x, then the slope of the line is simply tan of this angle, which is y over x. So let me ask you, what are the units of the modulus of elasticity? Any help? The modulus of elasticity, by definition, it is the slope of the line between stress and strain. The stress is in MPa and the strain has no units. So you can see here the answer. I'm asking a question while the answer is on the screen. That's funny. Now, anyway, so the modulus of elasticity is measured in Newton per millimeter square, same as the stress, which also can be measured in megapascal, MPa. And because the number, you will see the number will be roughly around 200 for steel, will be around 200,000. So sometimes people say, okay, why don't we say it in gigapascal? So easy to say 200 gigapascal. So which means it can be measured in Newton per millimeter square or megapascal or finally gigapascal. Now, this curve is, I think, one of the most important curve for me myself, okay, at least in this course. It's called the stress strain. And I want you to think about this one as a relationship between two variables like x and y. And so this relationship starts from 0, 0. Why is that? Because when we have zero stress, we have zero strain. You guys agree? If I don't apply any load to our specimen, do I get any strain? No. So that's why 0, 0 must start from 0, 0. Then as I increase my load, and remember the cross-section area in the beginning is constant, Constant. So as I increase my load, for sure the stress will increase. When the stress increase, the strain will increase in a linear fashion. And that's why you see the first part of the curve is straight. Between this point, I'm going to mark it for you. Between these 2 points is a straight line. And let me tell you, what is the slope of the line, which is the modulus of elasticity. So the modulus of elasticity, it is simply the tan of this angle right here. Tan of the angle, it means the opposite divided by the adjacent. It means if you take any 2 points, 1 point, 1 point, okay, 2 points on the line, you find delta of the stress. Like for example, you go here, you read the stress, you go here, read the stress one more time. Let's say this is 200 and this is 100. So this number will be 100, like 200 minus 100. And then you go down, like here, you go down and you measure 2 numbers or read 2 numbers, the epsilon here and the epsilon here from the scale. Simply this distance will be the difference in epsilon or the strain. So simply take any 2 points on the line, find the change in the stress, divide by the change in the strain, and this will give you the slope of the line, which is the modulus of elasticity. If you follow this discussion, please give me thumbs up. By the way, the modulus of elasticity, it should remind you with something you study back in your physics class. You guys remember the spring? You have a spring, hold with a mass, and then there is a K, something called the K, and K is the spring constant. This is, I don't know, like it's kind of a physics class, huh? The displacement is in proportional with the force. So the more you add weight into this hanging spring, the displacement will increase linearly. And the proportional constant is called K. Some people, they call it Young's modulus even, Young's modulus. If you remember this name. Anyone remembers Young's modulus? Young's modulus? All right, so Young's modulus is exactly modulus of elasticity. So you know, it's a proportional constant between stress and strain. Now let's pass this point. What happens if I pass this point? This point, by the way, one of the most important points called yield point. Yield point. So let me tell you what does it mean yield. But before I do that, I want you to understand that this part is almost horizontal. Look at this segment of the curve is horizontal. What does it mean horizontal? Mathematically, it means without adding extra stress, we get more strain. Do you get that? Look, when the line is horizontal, it means the stress is constant while we increase the stress. If you agree, give me thumbs up. I'll show you the curve. This part is horizontal, which means the stress is the same while the strain increases. Remember, this is your strain or the strain on the horizontal. So the meaning of the yield is getting lots of elongation without having to add any force. Now, this yield, as per the specification, how can you find it? Because it's not really like theoretically, that's how we teach students. It has a line and it goes here like a horizontal line. This doesn't happen. It's always a curve, okay? And that's why to find the yield point, very simple. Watch me, please. You can see here. In order for you to find the yield stress, you want to go here on the horizontal with a value of 0.2% on the strain. Then draw a line which is parallel to the first line. You can see this red line right here. When this dotted line hits the curve, then go horizontal and you can find and read the sigma y. What is sigma y? It is the yield stress. One more time. You go here on this axis here, right here, you add or find a distance of 0.2%. So you get this point. Then you draw a line with my cursor, which is simply parallel to the original line. And this line will go all the way until you meet the curve, then go horizontal, and this defines the yield stress. If you follow, please give me thumbs up. Now, what happens after the yield? What happens after the yield? I'll show you what happens. So at this point here, there is something strange is going to happen. And you can see the curve will go up. What does it mean? It is called strain hardening. All of a sudden, out of nowhere, your metal will say, okay, no, I can resist more after yield. So it's already on yield. But after the yield, and this again, the reason for that, it's pure metallurgy. Maybe the crystal or the atoms of the metal is restructured in a way after the yield so it can take more load. If you know about this question, please let me know. I don't know, I'm a civil engineer. But what we can observe is that there is a curve going up, meaning I need to add more force to get more strain. Until the end, which is simply this point right here, and this point is where you start nicking. Okay, the peak, it's where you get the nicking. After nicking, what happens is the curve will go down, and so this area is called nicking. This area is called strain hardening, and this area right here, it has a name called elastic region. Can anybody tell me why it's called elastic region? The first part on the curve. Look at the name.
It'll go back to its original size after once the stress is taken off.
Thank you, sir. So the elastic region, it means if I decided to remove stop the machine, I stop the machine and release the load. You know what happens? It goes to exactly 2 inches like L node. Once you pass the yield point, you become into elastic region, which means there will be permanent deformation in addition to your 2 inches you start with. If this makes sense for you, please give me thumbs up. All right, now we're almost there. By the way, I know you'll get tired, but we're almost there. Now in the data itself, when you get it in the quiz, you will see the software will give you a couple of values. Will give you something called ultimate load, and something called breaking load. So those numbers will be on the data in the quiz. And remember, it's a force, okay, measured in kilonewton. I'm asking you if the machine can give us those 2 numbers, and I'm gonna tell you something. You think with my test, did I establish the entire relationship in the actual test I showed you in the video? Am I able to establish the entire curve or just part of it, and why?
Probably just part of it, correct?
Just part of it. Why is that, Russell? Can you tell everyone why we're able to only establish part of it, not all of it?
Because you need more data points.
Because I have removed the extensometer, which measured the strain. Remember, there is one variable. As soon as we remove the extensometer, it means one parameter cannot be measured. So we measured slightly after the yield, and then we have removed it. However, what you see on my screen is the theoretical curve, and the machine will give us 2 values, and that's something you will see on the data. 2 values written in numbers, not as a curve, like just numbers written. One is the ultimate force, and number 2 is the breaking force. And then you should be able to find the ultimate stress and the breaking stress. Can anybody tell me how? So I gave you a force, and you want to find the stress. Masoud, you seem to know that. How is that?
Could you just use the area of the object that you're testing to
yes,
find the stress?
The force
yes, sir,
over the area of the object that we tested.
Yes, sir. Thank you. So here we go. So anytime you want to find stress, you're going to find the force divided by the cross-section area, and the cross-section area is right here. So the A node is equal to pi multiplied by D node squared divided by 4. All right? D node squared divided by 4 multiplied by pi. And that allows you to find 2 stresses. One is ultimate stress, and the other one is called the breaking stress, which is on the curve. Where is the ultimate stress? Watch me, please. So from here to there, this is the ultimate stress. And from here to this, to here, there, this is the sigma breaking or the breaking stress. If you follow this discussion, please give me thumbs up. Thank you. Now, this curve, by the way, I didn't mention it, but it's for mild steel. Mild steel. So do we have one kind of steel? The answer is no. I'll tell you something just, and again, this is a side discussion. It's a side discussion. Metals in general, in their pure form, kind of useless. The metals in their pure form, kind of useless because they don't meet our requirement for construction. They are either too brittle or too soft. So we need to do something. And so over the years, people, they know about alloys. And what is alloy? Alloy is a mix between the metals together to achieve some properties. This example is already available in our daily life. For example, gold. Pure gold, you think is good or bad? It's very valuable for sure. But I'm saying, I'm thinking of making jewelries. Is it good or bad?
It's not really useful. No.
Not useful because it's very soft, very soft. So how we can make a beautiful jewelries is by adding to it copper. Okay, so we mix them in a percentage, and it gives us different grades of gold. And copper makes it hard and make it easy to make those old beautiful designs. Same as the steel. Steel, depending on the composition, we get different properties. So what you've seen with me so far is something called the mild steel. So the mild steel is low to medium carbon. And so it's about 2% by weight. So we add carbon, okay? So carbon improves the mechanical properties of the steel. So it's iron plus carbon, 2% by weight, we get mild steel. Okay, now I'm gonna show you right now, and you've seen, the mild steel has ductility. It goes through the yield process. So now under the same machine, we can test another kind of steel called cast iron. Cast iron. So the cast iron has different composition, and you can read it down the curve. It has about 2 to 4% of carbon. So we increase the amount of carbon, and also we add silicon 1 to 3%. So I want you to understand that cast iron is not like mild steel. We change the chemical composition, and that's why the metal will react differently, and you will see that very shortly. So the curve for cast iron, it looks completely different from our mild steel. So how it looks, you can see here, the linearity is very unnoticeable, okay? So only very small part of linearity, but then it goes for a curve, okay? Do you see the yield? Anyone, please tell me, do you see any yield? Yes or no? Remember, the yield is horizontal. Once we see horizontal part, it means lots of elongation with the same level of stress. Do you see any yield? No.
No.
So cast iron is brittle. It doesn't, please write it down, it doesn't nick, so there is no nicking. It is very brittle, and there is no yield. However, for design purposes, people do want to see number, which is not really the yield, but for kind of taking a factor of safety from the ultimate. Okay, so cast iron does not yield. Mild steel does. Cast iron is brittle. Mild steel is ductile. So there is lots of elongation because we have the yield. However, although I just said there is no yield, however, in order for you to find an equivalent value of the yield, you do the same thing as mild steel. Remember, we take 0.2%, we create a line tangent to the line, and this cuts the curve. The difference is in cast iron, the number is different. Instead of 0.2%, we do 0.05%, 0.05%. And so we get this line, we create a line tangent to the first tangent, and when this line intersects with the curve, I go horizontal, I read the yield. So please write down that the only difference is this value. For mild steel is 0.2%. For cast iron is 0.05%. However, the idea is the same, where you can find also three things. You can find sigma y, and also on the chart you will find F breaking an F ultimate where you can find sigma breaking, sigma ultimate, same as we did with the mild steel. Now, last, we're almost there, huh? We're almost there. I'm asking you, what do you think about ductility? Ductility, like the word ductile against brittle. You think ductility for structure reason is good or bad? Any thoughts? Like when you build a structure like a rebar or a structural steel, you think ductility is good or bad? If you don't know the answer, I'm going to show you the video, but let's get your feedback.
To a certain degree, it's probably good to have.
Yes, sir. To a certain degree. Now, if you didn't get why ductility is important for structural purpose, I have a video for you. The video is about reinforced concrete beam. I'll show you shortly a beam, and the beam, probably I'm gonna, because it's a kind of very long video, and you know what, I'm gonna show you the beginning and then I will skip a little bit just to save you some time so you can work on your quiz number 2 instead of you working on outside the class. So I'm trying to save you some time, but I'll come back after the video and discuss with you what is the importance of ductility. Is it good or bad? Is it important, not important? Let's watch this video.
Like 110 to 160.
Okay, so I stopped here to show you. Do you see this crack? Can I get some confirmation, please? Do you see this crack at the bottom of the beam where you have tension stresses?
Yes.
Yes, okay, let's move on and see the rest of the video. Right. So our beam has already failed. The beam is already failed, okay? And I want you to just kind of remember what happens. So initially you get one crack, and then until the rebar at the very bottom start to yield, where the cracks get wider and wider and the beam gets a lot of deflection, so it will go down very noticeable. Huh? Now, question for you is, what do you think about this process? Is that good or bad? Why? Like if you think about it, I'm gonna make it different way. Think about you are in a building. You are in a building and the beam is about to fail, but the beam gives you all those warning before it fails. Lots of crack, lots of deformation.
When we have a lateral external forces, like as an earthquake, is going to give you a time to actually run away or get in a safest place and just go outside.
Or yeah, you're right. But or if you see that this beam is failing, probably you will add extra support until you repair it or do something. Okay. However, I want you to think, what if we make our rebar out of cast iron?
It's going to fail in a second.
Right away, you don't see anything right away. Without yield, it will fail right away. So I want you to know the following, that ductility for structural design purposes is very important. We need something that is ductile. The reason why it's ductile, because it gives us lots of cracks, lots of deformation, lots of sign before it fails. Now, I have done the discussion. There is one quiz, which is quiz number 2. The quiz has some question, which is theory about what we discussed today about the designation of the test, etc., etc., etc. And it also, at the end, it has some calculations about calculation. You know, calculations are very simple, by the way. And I want to recommend you to take a look at this. So I'm going to show you on my D2L. On D2L, so if you go to the D2L, you will see under the content. Under the content, you can see here there are a couple of files. One, it's called 2SMTL246 Lab 3, and that's the presentation I went through. I just finished. However, also what you see is strengths of material lab number 3 tension worksheet. And I told you this worksheet, it was the old way on how students they answer the questions, which I am planning to eliminate this 100%. So everything will be a D2L quiz. However, this document here is still a valuable document. So please write down. I'm not asking you to fill this. You will find this in your quiz. Don't do anything here at all. But why I'm saying that this document is valuable is because you can see it contains the math. For example, if on the quiz is asking you to find the original cross-section area A node, how can we do that? Any help? How can I find the original cross-section area A node? Any help?
Yeah, that's a pi over 4. It has a diameter, a squared diameter.
Okay, how can we find the final cross-section area? Right here. So please I don't want you to submit this document. However, this document is valuable because it shows you kind of the steps to answer the quiz. Don't answer anything here. So I'm not asking you to print this one or no. You will have to go through the quiz. As I said, the quiz has some theory questions, then followed by some calculations. You need some math. The math is right here in this document. Very simple, by the way. Find area, find the percentage, and then finding the 3 numbers, which is sigma y, sigma ultimate, sigma r, which is the yield stress, the ultimate stress, and breaking stress. Nothing's new. Any thoughts, any question? The original diameter, it's given in the quiz. So we've done this some measurement, And if the quiz gives you 3 numbers, you know what to do. If the quiz gives you 3 numbers, it means you need to find the average of them. And based on the average, you find the cross-section area. Are you following? So if I give you 3 numbers of the diameter, all you have to do is find the average, so the average of D node, then going forward, use the average of D node in finding the cross-section area, and then the ultimate stress, and then the breaking stress. If you follow this discussion, please give me some appreciation. All right, so now I know that there's still some time, so it's totally up to you. You want to split into groups, we have the groups for you. So split into the groups, okay? Again, I allow you, discuss, find the answer. That's okay by me until you submit the quiz. Again, the quiz is not up, deadline is not now. So you know, deadline is still far ahead. Let me check what's deadline for the quiz number 2. I can find out, that's easy. So if you go to tests, you see down here, you see lab quizzes, and it is due to February 25th. So that marks the Friday of the reading week. It's still long, still from today, there is 25 days. But what if we can finish it and then we can focus on other things? It's up to you. Any question? Thank you so much. And as I said, please make effort if you want. Come on Wednesday to see all the 2 tests live face-to-face. Thank you so much and have a wonderful day.
Thank you, Tahir. Have a good